Welcome to this explainer. Grab the nearest pen. Seriously, look at it. You probably have one sitting within arm's reach right now. It's so completely mundane, so everyday that it's practically invisible to us, right? But here's the truth. That little plastic tube is an absolute marvel. It's a jaw-dropping story of historical survival, high-stakes escapes, and hidden, microscopic engineering that literally harnesses the laws of physics just so you can jot down a grocery list. Today, we're going to shrink down to the microscopic level, walk the floor of modern industrial factories, and uncover exactly how this vital tool evolved. To truly appreciate what's in your hand, we have to look at this incredible timeline. And I mean, we're starting way back, 3000 BC. Ancient Egyptians at Saqqara weren't just carving stone, they were engineering the very first writing tools, using sea rush, specifically Juncus maritimus, to craft delicate reed pens. Fast forward a few millennia to 1827, and we see a Romanian student in Paris named Petrache Poenaru patenting a fountain pen that actually used a quill as an internal ink reservoir. Pretty cool, right? But the real high-stakes thriller of pen history, that goes down in 1938. A Hungarian journalist named László Bíró noticed something. The ink used in newspaper printing dried instantly. No smudging. He desperately wanted that same performance in a pen. So, working with his chemist brother, he patented a totally revolutionary ballpoint design. But history had other plans. Fleeing the terrifying advance of Nazi Germany, Bíró and his partners escaped to Argentina, where in 1943 they filed another patent and dropped the world's first commercially successful ballpoint pens. I mean, talk about writing history under pressure.
Okay, let's dive into this. Section 1. Engineering the 5 main types.
To understand how László Bíró's invention and the tools that followed actually work, we need to completely shift our perspective. Imagine shrinking down to the size of a dust mite. We're going right under the hood to see the cinematic, mechanical ballet happening at the very tip of your pen. Now, there are 5 main types of pens we use today, and the engineering behind them is honestly astonishing. Let's start with the classic ballpoint. Picture an extreme microscopic close-up of the pen's tip. What you're looking at is a perfectly machined sphere, usually made of brass, steel, or incredibly hard tungsten carbide, sitting beautifully in a specialized socket. This tiny ball is usually just 0.5 to 1 millimeter in diameter. But here is the absolute genius part. The surface of that tiny sphere? It isn't perfectly smooth. No way. It's intentionally covered in microscopic pits. As you drag the pen across paper, the ball rolls. And those tiny pits act like little buckets, scooping up a highly viscous, fast-drying, oil-based ink paste from the reservoir and depositing it right onto the page. It dispenses the bare minimum amount of ink required. And that is exactly why it doesn't smudge and why a single ballpoint pen lasts so incredibly long.
And this brilliantly illustrates the aha moment of why different pens feel so completely different when you write. You know that feeling when you switch from a standard ballpoint to a roller ball or a gel pen, and suddenly it feels like the pen is just gliding effortlessly across the paper? That is entirely about fluid dynamics. A ballpoint uses a thick, sticky, oil-based paste. But roller balls and gel pens, they use a water-based fluid, where color pigments are actually suspended right in the gel. Because the viscosity, the thickness, is so much lower, the ink is absorbed by the paper to a much greater extent. That's what gives you that incredibly smooth, effortless writing experience without having to press down hard at all. Section 2. Gel inks and left-handed logic. Now, let's talk about how this fluid chemistry solves a very specific real-world frustration. If you're a left-handed writer or you know one, you know the absolute misery of smudged ink. For lefties, as their hand naturally drags across the freshly written text from left to right, slow-drying ink becomes a smeared disaster. Enter the modern gel pen. The ink in a gel pen sits right in the sweet spot. Its viscosity is lower than ballpoint paste, but higher than liquid fountain pen ink. But the real engineering lifesaver here is the chemistry. These quick-drying gel pens are formulated with special solvents designed to evaporate rapidly, literally the second they hit the paper. It drastically reduces smudging, completely saving the day for left-handed writers and fast note-takers, while still delivering those bold, vibrant, opaque lines that people absolutely love for precise journaling. Section 3. Fountain pens and capillary action. But what if we remove the rolling ball entirely? Let's transition to the grandfather of modern luxury writing, the fountain pen. It brings up a really fascinating physics question. How does liquid ink continuously flow perfectly from a reservoir down a piece of metal and onto paper without just gravity dumping and spilling everywhere? Well, the answer is capillary action. Imagine a cinematic visual of water-based ink flowing flawlessly. Driven by gravity, the ink leaves the reservoir, but then it hits the feed, a specially shaped block with incredibly precise microscopic channels and grooves. These narrow spaces literally grab the liquid, pulling it along through capillary action, directing it perfectly into the tiny slit of the metal nib. When you touch that nib to a porous surface like paper, the capillary action transfers the ink out of the slit in a perfectly controlled line. There are zero moving parts. It is just pure, elegant physics. Section 4. Capillary action in markers. Now, what's really interesting about this slide is that you might think capillary action is reserved for fancy fountain pens, but it's actually the hidden engine driving one of the most rugged everyday writing tools in your office, the marker. They rely on the exact same physics, just engineered through a totally different medium. This completely shatters a common illusion. Most people assume a marker is just a hollow plastic tube sloshing around with liquid ink. It's not. Inside the barrel of a marker is a densely wound cylinder of polyester fiber. It basically acts as an incredibly precise capillary sponge. The density of these fibers is carefully engineered. Too tight, and the tip starves for ink. Too loose, and the pen floods your whiteboard. This fiber network regulates the ink flow through capillary action, releasing it to the nib by fiber-to-fiber contact, completely preventing the pen from flooding, skipping, or drying out prematurely. Section 5. 6 stages of marker manufacturing.
Knowing how precise this internal sponge has to be, you can imagine the sheer mechanical chaos of trying to manufacture these things at scale. Modern industrial pen factories are rapid-fire marvels, capable of turning out anywhere from 30 to 120 units a minute. The process is a relentlessly fast 6-stage mechanical ballet. Let's go through it. First, the barrels and caps are injection molded at extreme temperatures. Next, the polyester fiber tips are formed and baked. Then comes stage 3, and this is the most delicate step: reservoir insertion. The machine has to shoot that polyester fiber sponge into the barrel with pinpoint accuracy. If it's even slightly off-center, it crushes the fibers, completely ruining the capillary action and instantly killing the pen's ink capacity. Assuming it goes in perfectly, stage 4 injects exactly 1.5 grams of highly formulated ink to saturate the sponge. Finally, the nib and cap are assembled, inspected for perfect alignment, and packed. The whole shebang happens in the blink of an eye.
And all of this high-speed manufacturing is deeply rooted in material science. As manufacturing engineer Marcus Horn notes about injection molding the pen barrels at roughly 230 degrees Celsius, the polypropylene shaft is perfect for our pen. It feels warm and it's bendy. That warmth, that slight flexibility, that's exactly what makes the final product feel comfortable, ergonomic, and perfectly balanced in our hands during a long day of taking notes. Let's move to and see how this builds. Section 6, the 100 billion pen milestone. When we zoom all the way back out, from the microscopic pits on a tungsten sphere to the precision fiber sponges on the factory floor, we hit a massive global scale of everyday pen consumption. 100 billion. I mean, just let that staggering, jaw-dropping number sink in for a second. That is the estimated number of BIC Cristal ballpoint pens sold globally since their inception. It firmly cements this specific pen as the world's most widely used writing tool. Literally 100 billion perfectly machined little metal spheres spreading ink across the planet. So the crucial point is this: a pen is never just a pen. It's the culmination of 5,000 years of human history, surviving wars and border crossings. It's an absolute masterclass in fluid dynamics and hidden microscopic engineering. It's a tool constantly evolving to overcome our everyday frustrations. And it drives a massive, multi-billion-dollar global industry that keeps the modern world organized. Every single time you pick one up to scribble a thought, you are holding thousands of years of science in the palm of your hand. Which leaves us with a fascinating thought. In a world that's increasingly dominated by glass touchscreens, voice-to-text, and mechanical keyboards, what does the pen of the future actually look like? Will material science give us something entirely new? Or did we already perfect the delivery of human thought the day we mastered capillary action? Thank you for joining this explainer. Keep wondering, keep writing, and we'll see you next time.